This is EE698I, mixed signal IC design, and this is lecture number 9. In the last couple of classes, we discussed about how to characterize the performance of an ADC. Right? And we saw that for dynamic characterization, we apply sinusoidal signals, and we have metrics such as the signal to noise ratio, signal to noise and distortion ratio, dynamic range, and so on. Right? Similarly, for DC inputs, for characterizing the nonlinearity, we have the differential nonlinearity DNL and the integral nonlinearity, that is INL. Okay, so this is the static characterization for the ADC. So there is one last thing I would like to add to this part, which is the following. If you take INL, so how you find INL is that we take the input voltage, sweep it to different all possible values, and record the output, right? And ideally, you get some kind of a nonlinear curve like this, right? And INL is a metric of how much this transition points in the characteristic deviate from the ideal transition points. That is essentially this distance, right? For each code, this distance gives the INL, right? And this curve says how the output varies as a function of the input, right? So this essentially captures the effect of the nonlinearity, right? So as a result, this signal to noise and distortion ratio and the INL, they are not independent, okay? This should not be a surprise because both SNDR and INL, they capture the nonlinearity effect of the same ADC, right? So this is about the performance characterization of the ADC, okay? And if you take the data sheet of any ADC, you will find all these parameters mentioned, and you should be able to understand what each of them is and what is their significance. Fine. So till now we have been looking at the ADC from a system level point of view. So now it's time to get into circuit level detail and see how we can start designing them. And before that, let me explain one more thing. So let us say you have an ADC and it takes a single-ended input, say I call it Vin, and digitizes this input. Okay, and let us say it is operating from a supply VDD and a ground. Okay, and this is how most ADCs are. We just have one positive supply on which the ADC operates, right? And since the minimum voltage is 0 here and the maximum is VDD, this input voltage can span all the way from 0 to VDD. Okay, and usually this input will be given over a common mode voltage. Okay, and this common mode voltage, which I call VCM, is usually in the middle, right? So it is roughly VDD. I mean, it is usually VDD by 2. Okay, and the input voltage can swing over this common mode voltage, right? So the input voltage, how can I write? It will be VCM, that is the common mode voltage, plus some delta Vn, right? And what is the maximum amplitude of the sinusoid you can apply for delta Vn? Well, this is VCM. VCM is indeed equal to VDD by 2, right? So the maximum sinusoidal amplitude you can apply is VDD by 2, right? If you do that, the sine wave does something like this, right? So it reaches all the way at the top to VDD, and at the bottom side, it goes all the way to 0. Okay. Now, similarly, if you have an ADC that processes differential inputs like this, Say call this V1 and V2, and say it operates from the same supply, VDD, and you have the ground. Okay. So again, these two voltages, V1 and V2, so they can span from 0 to VDD, right? So this is 0, say, and this is VDD, right? And how will these two inputs be given? V1 will be the common mode voltage, that is this mid voltage, VDD by 2. This is also VDD 0, right? PCM plus some delta V in, whereas the other differential input will be VCM minus delta V in. Okay. And again, what is the maximum sinusoidal amplitude you can apply? That will be same as this, right? VDD by 2 sine omega t is the maximum sinusoidal signal you can apply, right? So you'll have some signal like this here. And for if this is V1, how will V2 be? It will be something like this. Okay, so let's say it's going all the way to 0. Okay, so if you take the differential input V1 minus V2, what you get 2 delta V in. That is essentially VDD sine omega t. Okay, and this differential input goes all the way from minus VDD to plus VDD, right? So this is the differential sinusoidal signal that is fed to the ADC. So let me draw it more properly. Okay, so this is the full scale range for the ADC, right? So from minus VDD to plus VDD is the full scale range for the ADC. Okay, so if you recollect, we have been considering that the range for the quantizer was minus Vref to plus Vref, right? So essentially this means that Vref is equal to VDD here. Okay. So now let's start getting into the details of circuit design. And we know that the first step in the ADC is to sample the input, and then you do the quantization, right? And this is the overall ADC. So let's see how to implement the sampling operation. Well, as the symbol suggests here, we need a switch for sampling the input, right? So let's say this is my analog signal, the continuous time signal Vin of t, and we are going to sample this using a switch, and the switch will be controlled by a control signal, which I'll call it as phi. Okay, and the samples of this input voltage, we need to store it so that we can do further processing or do quantization directly on them. Okay, so to store the voltage, we need to have a capacitor, right? So let us say, okay, so here what we need to make sure that we are sampling the signal at time instants that are spaced Ts apart, right? So the time interval between two samples must be Ts, right? This is the sampling rate. So which means the control signal for the clock must be a signal like this, which has a period of Ts, right? So this is the clock that is controlling the switch phi. Okay. So now let us say my input signal is doing something like this. Okay, so what will be my output? If I call this as the output, how will it look like? Well, during this phase when the clock is high, the switch is closed, so the input is completely shorted to the output, right? So let me mark this time instance also. So during this phase when the switch is on, the input is shorted to the output. So the output will simply track the input voltage, right? And at this instant, the switch is turned off. So the capacitor will retain the voltage this voltage, right? And it will hold it for the remaining phase, that is during this phase. Okay. Again, when the clock goes high, the switch is closed. So the input will be shorted to the output. So the output will again start to track the input. Right. So we'll have something like this. Again, here the output will be held, and here it will start to track the input, and so on. Okay. So this circuit operates in two phases, right? So in the first phase, we are tracking the input, and in the other phase, the input is held, right? So this is also called as track and hold circuit. Okay. And please notice that during the track phase, the output tracks the input, right? So at what time instant the voltage across the capacitor is frozen? At this instant, right? So the moment the clock falls to low, the voltage across the capacitor is frozen, right? So basically these falling edges are the sampling time instants. Okay, so these are the sampling time instants. Okay, and usually we have both track and hold to be of the same duration. So if the total clock period is Ts, we have a time interval Ts by 2 allotted for tracking, and the remaining Ts by 2 for holding. Okay, so the first Ts by 2 is for sampling or tracking the input. Okay, and we have one more interval of Ts by 2 in which the input is held. And in this phase, you can do further processing or directly quantize the samples. Okay, so this is the hold phase. Okay. So this is our track and hold, the input, output, and the clock. Right? So let's see how to implement the switch. And of course, you guys must be knowing that the simplest device is a MOSFET. Right? Okay, so this is going to be my input and this is the output. So let me just push it down. This is the clock signal. Okay. And historically speaking also, MOSFETs were invented to act as a good switch, right? So now to have the off, to make sure that the switch is off, that is to make sure that the MOSFET is off, we need to make sure that it operates in the cutoff region, right? And in the cutoff region, the gate to source voltage will be less than VT. So we need to make sure the gate voltage is the minimum voltage to make sure it's completely off, right? And since we will be operating from 0 to VDD, the gate voltage, which is same as the clock signal pi here, that will be 0, right? And similarly, when we wanted to turn the switch on, what will happen? The MOSFET will start conducting. And in what region will the MOSFET be operating? Well, if you observe, when the MOSFET is on, the out will be approximately equal to V in, right? So that's the whole point of using the switch. We want the switch to conduct and pass this voltage to, and pass the voltage to V out, right? So which means the drain to source voltage of the MOSFET will be approximately 0. So it's going to be in triode region, right? And of course, to make sure that the switch is on and it is in triode region, we pull the gate voltage, that is the clock, to the maximum voltage, and that is VDD, right? So the clock signal to this MOSFET should look like this. should go from 0 to VDD. And this is the time interval, which is equal to the sampling period of TS. Okay. So this is a humble track and hold circuit using a MOSFET. Well, if this worked perfectly without any issues, you'll have a lot less to study in the course. But unfortunately for you guys, that is not the case. And this comes up with its own set of problems. Okay. And luckily there are problems because only then as designers we'll have some job, right? If it's also simple, we'll not have any job. So only when there are some problems, we can come up with some solution and things get interesting, right? So let's see what possible problems can be there in this simple track and hold circuit. So let's see what are the non-idealities here. So firstly, when the MOSFET is on, what do you think can happen? What do you think can go wrong? Or what can be the problem? Well, ideally, when the switch is on, we want the resistance of the switch to be 0, right? We want it to be acting like a short between the input and the output. But of course, when we have a MOSFET, we'll have some finite resistance when it is on, right? So the first issue is finite on resistance. And next, this MOSFET will generate its own noise because of the thermal energy that the electrons in the channel has. Okay, so we'll see that when we sample the input, we'll also be sampling the noise that is generated by the MOSFET. Okay, so this noise is the second issue here. Okay, and when the MOSFET is on, so let me draw it here again. So essentially this clock signal is fed to the gate here, right? So we know that for the MOSFET, we'll have parasitic capacitors across all the junctions. So we'll have this capacitance between gate and this terminal. So when the MOSFET is on, what happens is, along with the input, we also have a path for the clock signal to feed to the output, right? So because of this, we'll have what is known as the clock feed through. Okay. So next, when the MOSFET is going from on to off, ideally, what we want is a clock signal like this, right? It starts from 0 and it jumps to VDD instantly and has this kind of abrupt transitions. But in practice, we cannot have this. So we'll have this kind of a slow transitions, right? And we know that for the MOSFET, we need to have the gate to source voltage less than threshold voltage, right? Threshold of the NMOS, right? So here the gate voltage is what? It is this signal, right? So I'll just call it as VG of t, or I'll call phi of t, minus source voltage is what? Source voltage is V out, right? But we know when the MOSFET is on, V out is roughly equal to V in. So I'll just say it's roughly V in. Okay. And only when this becomes less than VTH of n, the MOSFET turns off, right? And because the clock is taking some finite time to go from VDD to 0, the exact instant the MOSFET turns off will also now be dependent on the input signal, right? And please recollect that the sampling instants were the falling edges of the clock. Okay, so which means that is the falling edge. What does it imply? It implies the point where the MOSFET is turning off, right? So now that sampling instant is going to be dependent on the input itself. Okay, so this is called the signal dependent sampling instant. Okay, and when the MOSFET turns off, ideally we want this MOSFET to be out of picture, right? And this input and output must be isolated, right? But again, due to parasitic capacitance from drain to source, right, we have a path for the input signal to leak to the output. Okay, so this problem is called hold mode leakage. And lastly, when the MOSFET is on, right, when the MOSFET was, let's say, initially on, it will have a channel developed and the channel will have some charge, right? But now when the MOSFET turns off, the channel charge must go to 0, right? So where will the charge go? It'll, I mean, you will see later that this charge can actually go and disturb this capacitor charge. So this will in turn change the voltage that is actually sampled on the capacitor, right? And this is called charge injection. Okay, so we'll discuss all these effects in detail and see what these actually cause and how to overcome or suppress their effects. So let's start with the first non-ideality, that is the finite on resistance. Okay. So what does this mean? The switch has some finite resistance when it is on, right? So for simplicity, we'll say that we are modeling the MOSFET like this. It is an ideal switch to which we add a finite resistance, say R1 in series. Okay. So this is the capacitor. See, this is input and this is output. Okay. And please note that in practice, let's say this track and hold is used here in the first stage where it processes the input directly. Okay. And you will see in the later classes that the output of this track and hold might be resampled by some other track and hold, okay, for doing some more processing later. Okay, and now here this input signal can be varying, right? But we saw that the output of the track and hold is some kind of a held signal, right? So it tracks the input and holds it during half the period, tracks it, holds it, and so on, right? And when do we process the output of this first track and hold? When its output is held, right? Because only after this time instant the output is sampled, and during this phase when the output is held is when we can process this data, right? So the sample and hold, so the track and hold used in the second stage here will see an input that is kind of constant. Okay, so we'll analyze this finite on resistance effect for two kinds of input. One, when the input is constant, or you can take it as a DC signal. And in the other case, we'll consider a time varying signal. So let's start with a DC input. So let's say I have some DC signal here, V0. I have a switch. I have this resistance around. And then I have the capacitor here, right? And when the switch is turned on, okay, it connects here. And let's say the switch is turned on at t equal to 0. Okay, so this is the clock signal controlling. So let's say, oops, this is my instant t equal to 0. So which means this is Ts by 2. And this is Ts. Right? So let's say the input is this value. Okay, so this is say V naught. Okay. So how will the output look like? Well, because of this finite resistance R on, the capacitor voltage, that is the output voltage, V out, it will do something like this, right? It will charge slowly with a time constant given by R on C, right? So what is V out of t? V out of t is V naught times 1 minus e power minus t by tau, where tau is R on C. Okay. And when are we sampling the output? We are sampling it at this time instant, right? Ts by 2. So what we are interested is the output voltage at the time instant t equal to Ts by 2. Right? And what this is V naught times 1 minus e power minus Ts by 2 tau. Okay. So ideally, we wanted the output to be equal to this value, right? V naught. But instead, it is this value, right? That is the ideal expected value times 1 minus e power minus Ts by 2 tau. Okay, so this results in some kind of a small gain error, right? And in most cases, a small gain error is usually tolerable, right? And this might not be a big problem. Okay, but in some applications, let us say you are very interested in making sure that this error is very small, what you have to do is the following. So here I can split the output like this, right? So V naught minus V naught e power minus Ts by 2 tau, right? And if I write what is tau, it's simply R on times C, right? So if you want to make sure that this V out sampled at Ts by 2 is exactly equal to V naught, what we have to make sure? We need to make sure that Ts by 2 R on C must be much greater than 1, right? And in practice, if you choose some value for this ratio, I mean, for this fraction to be around 5 to 10, it might be fine. But if you are even, if it becomes very critical in some applications, you need to increase this ratio even higher. Okay. So now let us see what happens when we apply a time varying signal. And for simplicity, we'll assume that we are dealing with a sinusoidal signal, because of course any signal can be decomposed as sum of sinusoids, right? So let's say I have a sinusoidal signal, say V naught cos omega t, that is given to the circuit. Okay, so this is R on and this is C. Okay, and let's assume that the switch is closed at t equal to 0. Okay. And let's assume that the capacitor is initially discharged. Okay, so that was the assumption that was made here also, right? So we assume that the capacitor initially had 0 charge. Right, so how will the output look like? V out of t. Well, the output will have some transient plus a steady state component, right? So the transient component, which I'll just call VTR, it will decay, right? It will decay with the same time constant, e power minus t by tau. Plus we'll have some steady state component. Okay. And how will the steady state waveform look like? Well, we are giving a sinusoidal signal. So the output will again be a sinusoidal signal of the same frequency. So we'll have cos omega t. So what will change will be the amplitude and the phase, right? So how will the amplitude change? The input amplitude was V naught, right? And that will be multiplied by the magnitude of the transfer function of this system at the corresponding frequency. So I'll just write it as mod h of j omega, right? And similarly, we'll have a phase shift. We'll call it phi. And what is phi? Phi is the angle of the transfer function, right? So this portion, this transient portion, I'm not computing. So take it as an exercise and try to exactly compute what V out of t is, okay? Especially the transient portion. So now what is h of j omega here? It is simply the capacitance divider, right? I mean the resistance divider or the impedance divider. So 1 by j omega c by r plus 1 by j omega c. It is 1 by 1 plus j omega c. So magnitude of h is 1 by, sorry, this is r on, right? So this is r on times c. This is 1 plus omega square r on square c square, right? And what is the angle? That is simply minus tan inverse of omega r on times c. Okay, so the final output voltage V out of t will be the transient component into e power minus t by tau plus V naught by square root of 1 plus omega square r on square c square cos of omega t minus tan inverse of omega r on times c. Okay, and of course we'll be interested in the sample at t equal to ts by 2. Okay, so we'll be interested in this value at t equal to ts by 2. Okay, but the important thing to notice is that here we have two error components, right? One is this transient portion, which is similar to the error we got here, right? So this will decay to 0, but we also see that the steady state portion, we have a scaling for the magnitude and we have a change in phase, right? And if you want to make sure that the this portion is equal to 1, right? So which means omega or on times c must be much less than 1, right? And this will in turn ensure that even this angle is equal to 0, right? So this means that 1 by or on times c, sorry, must be much greater than omega, right? So now if you look at the Bode plot of this h of j omega, how will it look like? It is a first order system, right? And it has a pole at 1 by omega r on c. So it will look something like this. So let me write h of j omega also. It's 1 by 1 plus j omega r on c. So if you plot the magnitude response, using the Bode plot, this is mod h. So it will be 1, right? That is say 0 dB in log scale. And then it will fall at a slope of minus 20 dB per decade. And this is what? Minus 1 by, or if I just write the magnitude of the frequency, it's 1 by r on c. Okay. So what we need to make sure is that this portion omega r on c must be less than 1, right? So we need to make sure that the maximum signal frequency, if I call it as omega max, okay, that should also be less than 1 by r on c, right? So we need to choose our signal frequency, maximum signal frequency, to be somewhere here, right? So this, we choose it to be, say, omega max, right? And usual thumb rule is to make sure that this is 10 times smaller than the RC pole location. Okay. So now let us say you're given a particular sampling frequency and you know what is the maximum input frequency. Okay, so you can find what is R on C, right? So either from this condition or from the settling error you got for the DC input, right? Whichever is a more stricter condition, you use it. And you'll find in many cases, this will be the most stricter condition. Okay. So you can find what is this time constant, right? And we'll see later that the value of capacitance C can be fixed from the noise criteria. So let us say this capacitance value is also known. Okay, this we'll see in a later class. But for now, let's assume that the capacitance value is also known, right? So which means we can find what is R on. Okay, so we need to make sure that our switch on resistance is the maximum value is equal to this or on, right? It can be less than that. It's not a problem, right? So let's see how to do that. And for that, first, let's try to find out what is the on resistance of the MOSFET. Right, so this was the MOSFET we considered, right? And when the MOSFET is on, the gate is connected to VDD. This is V in, and this is V out, and we know V out is roughly equal to V in, and the MOSFET is on, right? So since the MOSFET is operating in triode region, what is the current? Current is nu n COX W by L VGS minus VTH times VDS minus VDS square by 2, right? And of course, since V out is roughly equal to V in, the drain to source voltage is almost equal to 0, right? So I can simplify this to be nu n COX W by L VGS minus VTH times VDS, right? So what is the on resistance? It is dVDS by dID, which is simply 1 by nu n COX W by L times VGS minus VTH, right? And what is VGS? So I'll write this nu n COX W by L. So what is VGS? The gate voltage is VDD, right? And the source voltage is roughly V in. So it is VDD minus V in minus VTH. I'll just say it's VTH in to say that it's for PMOS. Okay, so I'll just change everywhere. VTH of NMOS. Okay. So now from this, you can clearly see that if you want to reduce the on resistance, what do we have to do? Well, first, this factor, mu n COX, is dependent on the process, right? We do not have any control over this. Okay, so we have control only for on this one, right? And if you want to reduce the on resistance, what we have to do? Well, we need to make sure that the length is the minimum length we can choose, right? So this we have to do for minimizing R, right? And of course, you also see that if you want to reduce the on resistance, we can also increase the width, right? But when you increase the width, what happens? All the parasitic capacitance associated with the MOS also increases. So all these capacitance, right, will increase, right? As a result, the non-idealities that we discussed earlier, that is this clock feed through or the hold mode leakage, everything will start to dominate. Okay, so there is some trade-off, right? We can't keep increasing the width forever. Okay, so this is something, but this is something that you should always be aware of, right? For a switch, you make sure that you use the minimum length because that's what will result in the smallest on resistance. Okay, but a more interesting thing is to note is the following, is that the on resistance is dependent on the input voltage here, right? So which means the on resistance will keep changing depending on the input voltage. So what do you think will happen? Do you think it is a good thing or a bad thing? Or what do you think will happen because of this? I suggest that you pause the video and think about it. Okay, so what we saw was the following. The on resistance or on was inversely proportional to this factor, right? VDD minus V in minus VTH. So VDD minus V in minus VTH in, right? And if you from the previous analysis, what did we see? When we apply some sinusoidal signal, the output, the steady state component is this, right? So let me just copy paste this. Right, so this is my output. Okay, and let us say I assume that this phase that is very small, so I can approximate it to be 0, and I'll call it to be this. Okay, so I can also simply write this as, I mean, this is just approximation, right? This I can write as V in of t by square root of 1 plus omega square or on square c square, right? And from here we see that R on itself depends on the input. Okay, so this is essentially V in of t by square root of 1 plus omega square, some function of input, right, times c square. Okay, so this obviously is not a linear relation between V out and V in, right? So this straight away introduces non-linearity. Okay, so if you take this track and hold circuit, okay, and give a sinusoidal signal, and if you take these samples and look at the spectrum, it will contain all the harmonics of the input frequency. Okay, so this is the R on, right? R on was inversely proportional to VDD minus V in minus VTHN. Okay, so which means for lower values of V in, okay, R on is small, right? R on is also small, right? But the moment you keep increasing the input voltage, what happens? The on resistance increases. And if you increase V in and tend it to VDD minus VTHN, what will happen to R on? R on will also tend to infinity, right? And this will no longer act like a good switch, right? So it's a switch with an infinite resistance, which is of no use literally. Okay, so if you give some sinusoidal signal like this, so let me draw it clearly. Okay, from let's say 0 to VDD, what will happen? Well, for smaller, I mean lower input voltages, the R on is also low. So we'll have a decent tracking of the input. So let's say it tracks something like this, and then it will hold. But as the input increases, it will not be able to follow, right? So maybe it will do something this. And when the input reaches maximum, it will not be, I mean, the resistance will be very high, right? So it will not be able to track at all, right? It will do something like this. Right? And again, when the input starts to decrease, it might be able to track decently. It will hold here. And as input reduces further and further, it will be able to track even better, right? It might do something like this. Okay, I'm just drawing some very rough sketch, right? And from this, you can clearly see that the input samples, I mean, the samples you get from the signal, they'll be completely distorted. Okay, because ideally what you expect the output to be this, right? Right, this is how it should ideally have looked like, right? So now let us see how to go about solving this problem. So the bottom line here is the problem of the on resistance varying as a function of the input, right? And we see that when the input is varying from 0 to VDD, the on resistance varies from some finite value, say R on, to infinity, right? It varies by a large, by a large amount, and that introduces nonlinearity. Okay. So one solution to this problem is to do the following. So for the NMOS switch here, when the input is close to VDD, it is a problem because when you apply VDD to the gate and try to turn the switch on, this gate to source overdrive will not be enough to turn the switch on, right? And that's what was resulting in a very, very large on resistance, right? So what you can do is the following: instead of connecting the gate to VDD, we can connect it to some higher voltage, let's say VDD hat, and that is greater than VDD. Okay, so this is a capacitor here, right? So for example, let's say your nominal VDD is say 1.2 volt. You can get supplies, let's say of 1.8 volt, and use it to control the gate of the NMOS. So instead of having a signal going from 0 to 1.2, now you'll have the clock that is fed to the gate going from 0 to 1.8 volt. Okay, so this way, even when the input is equal to VDD of 1.2 volt, since this VDD hat is 1.8 volt, the MOSFET can sufficiently turn on, right? So earlier, when we varied the input voltage from 0 to VDD, R on was varying from some value, say R on, to infinity, right? But now, or let's say it's exactly to VDD minus VTH, right? Because when it reaches this value, it was going to infinity. But now when you boosted the gate voltage, so with gate boosting, what happens to R on? When the input is 0, it is some R on 1, right? And this R on 1, it is lesser than this value you got for the earlier case, okay? Because you have increased the voltage to the gate, right? Remember that the on resistance was inversely proportional to the gate to source voltage, right? That is VG minus Vin minus VTH, right? And in this case, VG is VDD hat, right? Since we are using a higher voltage for this VDD hat, the R on that you get for this case, that is R on 1, will be less than the on resistance you got for the earlier case, right? And when you increase it to VDD minus VTHN, this is no longer going to infinity. It will be some R on 2. Okay. So this has not solved the problem completely, but has made sure that when you increase the input from 0 and move it closer and closer to VDD, the variation in the on resistance is reduced a lot. Okay. So this will help with the linearity to some extent. Okay. But the problem is, well, you might not be able to use this higher supply in all the designs, right? So only in some cases, you might be able to use this higher supply, and it is not possible to do in general for all designs. Okay. So let's see what can be done next. So we'll note now that for the NMOS switch, it is acting like a good switch, okay, for low Vin, and it cannot be used as a switch for a higher values of Vin, right? So obviously we expect that there should be some dual device that will do the opposite job. That is, it will be a good switch for high Vin, but a bad switch for low Vin. Okay. So I'll just put tick for NMOS. Right? And that dual device is what? It is the PMOS, right? And if you use a PMOS switch, you will have something like this. This is the capacitor. This is the input, right? And if you want to turn the PMOS switch on, what do you have to do? The gate voltage must be equal to 0, right? Similarly, if you want to turn it off, the gate voltage must be the highest voltage. That will be VDD. Okay. Because remember that for PMOS, you need to look at source to gate voltage. Okay. So what we'll do is we'll say that the clock here is phi bar, that is inverted version of the clock we gave to the NMOS. Okay, so because if phi is 1 now, that is phi is equal to VDD, which implies phi bar will be 0, and then the PMOS will be on, right? Similarly for the other case also. Okay, and what is the on resistance of the PMOS? I'll call R on P. That is 1 by mu PCOX W by L, source to gate voltage, minus mod VTHP. Right? We can derive it similarly to the way we did for the NMOS switch. And if you simplify this, what do you get? Mu PCOX W by L. What is the source voltage? It is equal to Vin, right? What is the gate voltage? Well, to turn the PMOS switch on, the gate voltage must be 0. So this is simply 0 minus VT mod VTHP. Okay. So from this, we can clearly see that for the PMOS, we'll have a good and low on resistance for higher values of V, right? And the moment the input voltage approaches close to mod VTHP, the resistance goes up to infinity. Okay. So now we have two devices. One that is a good switch for lower values, right? From, let us say, for this range, right? In this range, NMOS is a good switch, and for higher voltages, PMOS is a good switch, right? So to make sure that we have a good switch over the entire range, what do? We combine the two, right? So we put the two in parallel like this. Okay, so PMOS will be clocked by phi bar, NMOS will be phi. Okay, so this switch is called the CMOS switch, complementary MOS, or it is also called as the transmission gate. Okay, so now let's try to see what is the on resistance of this CMOS switch. Okay, and before that, please note that when we give an input voltage, this is the Vout, right? So for lower voltages, lower input voltages, what will happen? The PMOS will offer a very large resistance, right? So we'll have a very large resistance in parallel with the small resistance offered by the NMOS. So the NMOS will conduct, right? And similarly, when the input voltage is high, it's closer and closer to VDD, the PMOS will offer, sorry, the NMOS will offer an infinitely large resistance, and it will be out of the picture, and we'll have conduction through PMOS, right? And this way we have a good, reasonably good switch over the entire range, right? And even intuitively, we expect that the distortion we saw with only an NMOS switch must now be better, right? Well, with NMOS switch, we had distortion when the input went closer and closer to VDD. And with the PMOS switch, we'll have distortion when the input reaches closer to 0. So if you use a combination of the two, we at least qualitatively expect that this distortion must be improved, right? So let's try to verify that. For that, let's try to find the on resistance of this, right? And on resistance of the CMOS, which is what? It is the parallel combination of the NMOS and the PMOS switch on resistances. So I can write this as 1 by R on N plus 1 by R on P. Okay, and what is R on N? R on N is this guy. There it is. Yeah, it is this guy. And similarly, R on P is this fellow. So we'll put the two as this 1 by R on N is mu NCOX W by L. I'll say it's W by L of the NMOS times EDD minus Vin minus VTHN. Okay, this is 1 by R on N. Similarly, we have 1 by R on P, which is mu PCOX W by L of the PMOS times V in minus mod VTH. Okay. So now here, if you make mu n COX W by L times N to be equal to mu P COX W by L times P. Okay, and say I call this to be some beta. So what will happen? R1 will be 1 by beta times VDD minus V in minus VTHN plus V in minus mod VTHP, right? And we see that the dependence on V in completely goes away. Okay, so if you take this CMOS switch and design it for this condition, in principle, we will have no dependence of the on resistance on the input. Okay, so for any value of the input, the on resistance is going to be constant, and so we should not see any distortion. Okay, but obviously in practice we cannot guarantee this properly. Okay, because this mu n COX and mu p COX are dependent on the process. Okay, so if you design assuming that they are of some value, okay, and let's say you assume these to be of some value and choose your sizes W by L of NMOS and PMOS to be such that this quantity is equal. After the device is fabricated, you will find that mu n COX and mu p COX are totally different. Okay, so in practice, you will not be able to get this cancellation happening properly, and you will have some residual effect of V. Okay, but it will be smaller than when you had only for the NMOS or PMOS, right? So it will be definitely better, but you will still have some dependence on V. Okay, and usually mu n COX is roughly around 3 times the value of mu p COX. Okay, this is again some rough number. And so to make sure that this quantity is equal, what we have to do, we need to size the PMOS to be 3 times that of the NMOS, right? And we saw that for this switch, the length must be chosen to be the minimum length possible in the process. So this essentially means the width of the PMOS should be 3 times the width of the NMOS. Okay, and doing this will guarantee that to some extent the dependence of V in, the dependence of R1 on V in will be reduced. Okay, and so we'll have a better linearity, right? So with a CMOS switch, we definitely will have a better linearity than a simple NMOS or a PMOS switch. Okay, but in practice, there are applications where we need a very high resolution, and in those applications, you might need to have a much better linearity than you might get with the CMOS switch. So in that case, we will see what can be done, and we'll continue from that point in the next class.